Ladies and gentlemen, let's welcome up Teijen.
Okie dokie. So let's make sure this, booyah. So who am I? As I was introduced, my video game name is Teijen. I normally go by Logan. I'm a PhD student at UAH, and I'm just kind of a general goofball. You know, I like to have fun. So why are we here? Why does this talk exist? And it exists because reverse engineering is like a really difficult problem. The technical expertise required for people to professionally and proficiently do reverse engineering, requires specialized skill sets, large amounts of like training time, and frankly, by the time you get useful, you're a graybeard. That's just how it goes. And so vast man hours can't really attempt to fulfill the coverage scope of this problem. So people have naturally started to use AI to try to help automate and support the graybeards in their really intensive task. So what issue have I identified? So I find that there's like a fundamental oversight when people are building machine learned models for binary analysis. I did a whole literature review where I mapped everything out and I tried to figure out what is happening in the field, what is being supported, and what's going on. And so my main analogy for people who don't really know this field all that well is people build race cars, and they spend a whole lot of time on aerodynamics and driver testing and car shape and track design, but they, for some reason, didn't test their tires. So when we talk about underlying decompiler architecture, I want you guys to think about how we go from binaries in the wild to decompiled C or decompiled code or whatever you were staring at when you're trying to understand what these binaries are doing. And it's a process. You know, the decompiler can be the steering of the car, so to speak. It's like how you're feeling what the road is doing. But it's the entire suspension system from the ground up where the rubber, the tires, meets the road, that sort of enables that steering of how the road feels and like what decisions you make. And so the tires in this example is the intermediate representation that each compiler utilizes. So how do we solve this issue? We solve this issue by taking a known car with the car analogy. We take it on a known track, and then we just test different types of tires. And those different types of tires are different decompilers with different intermediate language representations. This is really a comparative study where we try to control as much as we can, and we take an apples-to-apples comparison so we know what's happening. Because that's like how science works. You know, fifth grade science fair, you have one independent variable and then a whole bunch of dependent variables. And so the independent variable in this scenario is the decompiler and its intermediate representation. This is the agenda. So I'm going to go over some like essential context for people who don't have the background. Here's definitions you need to know so the rest of the presentation kind of makes sense. Then we're going to talk about the control model. This is the car. This is what binary analysis task was chosen for all of the testing, how the testing went, and then some key takeaways that we can get from the testing. So what do you need to know to help have this make sense? First of all, you need to know what a decompiler is. If I'm saying this word decompile and you're staring at me like I don't know what that phrase is, it's something we really need to cover. So over here is the process of compilation. Compilation takes text files, code, and converts them into a workable binary that computers use to operate and perform tasks. It has all of these analysis phases, but the most important phase right here between code analysis to target generation for different types of computers is this intermediate code generation step that compilers convert all of their raw code into to act as a Rosetta Stone, a Rolodex of what architecture needs what to operate in. And so a decompiler does this process backwards in a very simple way. It takes a program, that complete box that does a task, and converts it back into readable code so that we, as people who are reverse engineers or malware analysts or are generally trying to understand what these black boxes do, can figure it out. So I'm talking about tires. What tires am I testing? Like, what decompilers am I choosing to use for this test? And so there are three. There's IdaPro, Binary Ninja, and Ghidra. The reasons IdaPro's been there forever. It's 30 years old. It's an industry standard. People utilize it heavily in a vast variety of use cases. Ghidra is the free version that the NSA released in 2019. It has allowed an explosion of talent to enter the reverse engineering field because it reduced the barrier to entry, so it is commonly used. And then Binary Ninja is an up-and-coming commercial premium version of IDA, but it's significantly cheaper, has additional features that they would like to utilize. But from a use perspective, it kind of hits that midpoint balance of like completely free, industry Goliath, industry startup that's really trying to be utilized and people see it. And I found it in the literature. What intermediate representation each uses, IDA uses microcode. Binary Ninja uses low-level intermediate language representation for the base layer, and Ghidra uses P-code. Binary Ninja has more, but because we're trying to go as low-level as possible, this is the lowest form of the intermediate representation that this one tool utilizes, so we're going to be talking about this one for the rest of the talk. To show kind of how they're different, I have examples for each of the three. Most decompilers and disassembly operates on an instruction, 2 operands, or 3 operands model. And so microcode and P-code are displayed in that format. You have operation codes, operation code, and then operands. Low-level IL, it's a little bit more abstract. It kind of follows like assignment and calls and some things that you would see in a higher level language, but it morphs up and gets more higher level as it gets taller, but this is their lowest level version, so it's a little bit more abstract compared to the other two. And then we got to know, how does machine learning even fit in? Like I've talked about decompilers, but this is the task, this is the driver of the car, this is what we're doing. And so we have to understand where the decompiler sits in the system. And so in this graph over here, you see this box where it's clean and transform before features and modeling and insights are extracted. The decompiler takes the raw data from all of the different sources, so in this case in reverse engineering, the binaries, and it cleans and allows feature extraction to occur of this decompiled code that they utilize. So it sits at this really precipice of how things are flowing into the system, and so when you're doing training data analysis and like how you want to interpret the data, it just has to go through this pipeline. It's like a fixed thing that you have to interact with at some point, so it leaves its mark as you continue forward through here. Here are some also simplified definitions for people who don't work in machine learning that would help understand this talk. Accuracy is sort of like your school grade when you're in a test. Out of the total number of guesses you had to make on a multiple choice test, how many of them did you get correct? Precision is how often your guess for a thing was right. This is different from accuracy because it's, hey, I guessed A on the multiple choice test. How many A's when I chose were correct out of the total number of A's that I guessed? Recall is sort of how many of the thing were you able to capture. So if you're trying to identify cats and dogs, and there are 10 dogs, and you were able to identify and say there were 8 dogs, then your recall is just 8 over 10 or 0.8. And then F1 score is a fun number that mixes precision and recall. Precision and recall are basically opposites because they operate on how much of the thing did you not misidentify versus how many did you miss. So if you are really concerned about making sure you capture everything, you're going to tune your model to perform a high recall. But then it might get it wrong. It might call some things the target that aren't the target, but you're okay with those misidentifications because one bad miss and causes a big problem. Or if you're like, no, I need to only identify the thing I need to identify when it shows up, and I don't care if I miss things, so I want to be 100% certain that I am identifying the correct thing, then you might tune your model for high precision, and then you're okay with missing some things in recall. F1 score is like a mix that takes that into account and how they kind of invert each other and creates a fun curve that you need to understand. And so then the machine learning algorithms we're going to talk about are basically different ways you can make the decision. So the 3 in this talk are going to be support vector machines, random forest, and k-nearest neighbor. They operate differently. They make decisions differently. Support vector machines in a 2-dimensional space is you draw a line, and the dot on one side of the line is class A, and the dot on the other side of the line is class B. The more lines, the more different classes there are. For random forest, it operates with a group of trees, like a Plinko machine. So you're like, this is my guess. I'm going to ping down the features and what the statistical likelihood of each feature is, and then each tree is going to guess. that it landed in class D or class B, and then whatever class is the majority voting from all of the trees in the system is the class that the machine model guesses. And then you have k-nearest neighbor. So I want you to imagine on an XY chart, each different type of thing sits on the chart somewhere. And you know this when you're labeling or you're telling the machine what things are. Then you plop a new dot on there. And whichever group that dot is in or closest to is the guess that that classifier determines what it is. So the control model that we use to test the car is malware classification uses static disassembly and machine learning by Chen et al. It was released in 2021. It uses more classical machine learning models. This does not include transformers because at the time when they were doing their research prior to 2021, because this is the published date, transformers just weren't available to those people and researchers at the time that they were doing them. But it's a control, so we know everything that it exists in, and we have the full understanding of what it was published in. So what does Chen et al. Even do? It takes groups of malware, and it says, hey, you're in group A, B, C, or D. It was made in response to Microsoft when Microsoft dumped 11,000 binaries on the internet and said, hey, whoever classifies them the best wins $100,000. So there was a large amount of incentive for researchers and individuals to figure out how do you classify malware with the data set that Microsoft has provided you. The questions in Chen et al. Is they focused on which model type classifies the best, so that random forest, that support vector machine, and that k-nearest neighbor. And they also asked which feature combinations make the best classifier. So this table here shows two things. One, it shows which features perform the best in Chen et al., which feature groupings, and it also shows their accuracy. This latest column is, hey, someone can write anything that they want. Can I prove that their thing works? So I took Chen's code, and I took Chen's training data, and I reran Chen. I reworked Chen. I said, hey, is your thing legitimate? And I was able to show that, yes, it was legitimate, which means the car works, so when I'm testing tires, I don't have a bum car. These three feature sets are highlighted because these three feature sets are the ones that are going to be impacted by a change in Decompiler. These are the feature sets that are going to be changed by the intermediate representation of the code. The reason that these three feature sets are changed is because they all include this base feature, the opcode foregram. The opcode foregram is the main feature that we were changing when we changed decompilers and when we were changing intermediate representations. What the opcode foregram is remember when I showed the column of operation codes? So you could have add, subtract, multiply, divide. That could be 4 operations in a row. You could have add, copy, delete, add. Those could be 4 operations in a row. And each one of those combinations becomes a unique group. And so the opcode foregram takes all of the unique groups in all of the binaries and converts them to a vector so you can determine which unique groups are present in which kind of binaries. Those unique groups change depending on the definitions of the intermediate representations, because each intermediate representation has different operation codes because it's like a vocabulary. It's like words are different in Spanish than words are different in English. And so if you have different words to describe the same idea, how they interact with each other will be different. Dimensionality is how, all of those unique features put together, drawn down to a reasonable amount, and it's based upon the individuals. So you have file size being a static one, API foregrams, which is external function calls. You have opcode foregram. Those all get pared down for all of the unique capacities in Chen's original work down to 5,000, just because it is computationally intensive, so you only want the 5,000 most prolific features, so you can get rid of outliers that are only showed up 1 or 2 times within the data set. This just makes it easier to separate binaries and classify them appropriately. So this goes over the malware classification data set. If we're classifying malware, what malware are we classifying? What did Microsoft release? So Microsoft released roughly 11,000 samples. It is an unbalanced data set. For those who don't know, in machine learning, you kind of want your data sets to be as balanced as possible when you have multiple classes being classified. It makes the decision boundaries more clear. So, but this is what Microsoft gave out. And the types, you have the family name and what its general type is. Worms, adware, backdoors, Trojans are all prevalent in the data set. The one that I think is more unique is they took all of the obfuscated malware that they could find anytime someone tried to hide something and it wasn't being direct, and they just shoved it into one class. That does come up later when we come to training results. And then for each sample, it's noted that there was a .bytes file and a .asm file. Basically, Microsoft didn't want to get liable for just releasing 11,000 samples of malware out to the public to download. So what they did is they sterilized it, and they released it with 2 files per sample. The bytes file is there's normally a preamble in executables, and they took that preamble and they cut it out so that way none of the executables could be run. That's how they sterilized it to keep it from wreaking havoc on a bunch of people's machines. And then the .asm file is a disassembly file generated by IDA, because Microsoft only wanted to release IDA disassembly files to the public so people could see other information about the file. So now that we've gone over what the car is, what is Chen, and we've gone over the problem, which is nobody is testing the different intermediate representations and how those different intermediate representations could impact the outputs of Chen, let's test it. So I just talked about how the training data was organized for people to put through. That training data doesn't really let you just throw binaries into these reverse engineering paradigms directly. So you have to do some conversion process. And there's some compromise there that is just inherent due to Microsoft sterilizing the data set. So I took the sample hexadecimal file because it contained all of the code sections of the data. It just wouldn't be able to tell me external references and imports and all of that nature. So we're really focusing on just opcode sequences that are prevalent in the code sections. And then I made it a binary. I put that binary into Binary Ninja for the low-level IL, the Binary Ninja process, and I looped through the detected functions from Binary Ninja. And then I saved it because each file is just a text file. So we end up just with text files of operation codes and the operations for each function as they're processed through the binary. Now, you might say that could change some things because the other two might not define functions in the same places. And I went, OK, so we're going to do the same thing. We're going to get Binary Ninja's function boundaries by their address, so the start and end of each function. And I'm going to tell Ghidra and IDA, hey, those start and ends are the functions. We're going to interpret them as functions, and we're going to interpret within the function as code. So that way we can get the operation codes for each decompiler and each IR lined up in order with the first one, so we compare apples to apples to apples for each function and each representation of each function. And then you loop through it, and you save the text files for the machine learning process to ingest. So this is where we have like cost and like things that people are engineers who care about. Like how long did this process take? Is one slower? Is one faster? Is one take up more room? One does not take up more room because these different representations can cause different output. So we talk about hours. Now low-level IL has an advantage inherently because it didn't. The other two had to go through the process where we tied functions together. But comparatively, you can see the 25-ish% increase between Ghidra with P code and IDA with microcode. And so it just shows that IDA might take longer to process binaries to output these operation codes. And then the bit more important difference is the converted training data size. So for all 11,000 samples in low-level IL has text files for each operation code for all of the functions caught. It took about 30 gigs. That's like not great, but OK, cool. For P code is much more verbose when it's going through functions. And so it took 5 terabytes. That's 2 orders of magnitude-ish, and goes from reasonable to very unwieldy and requiring external storage solutions quickly. And then microcode was the smallest at like 4 gigs. So if you're really struggling on space and you're trying to make an engineering decision upon, I have to store the output data of these decompilers, how am I storing it? Maybe microcode might be better for you because it just has a smaller amount of output. And now let's talk about training outcomes. These are the actual machine learning statistics that are output by the training. So this is all 3 function groups. Remember how I said there were 3 function groups? There was the opcode foregram, the opcode foregram plus the API foregram plus the file sizes, and then the all features group. These are the 3 groups that include opcode foregrams within the calculation, so that's why all 3 of these are included. So blue is bad, red is good. The more red, the better. If you're kind of in the middle, you end up like grayish white. And so this is a heat map that can kind of quickly draw people's eyes to what performed the best, what performed the worst comparatively. None of them performed bad. Like we're talking 0.96, 0.97. These are really high ratios. But when you're scaling from a small data set to the infinitely large data set of malware that exists in the wild, these smaller values can represent millions of dollars in compute time when you're expanding to these large data centers with large amounts of GPUs and large amounts of usage. So some key insights generated by this. In just opcode world, where we're just focused on the operation codes of the intermediate representation, pure low-level IL and binary ninja was the best at clustering. If you were focused on a clustering ensemble or you were trying to make decisions based on clustering, it performed way better compared to the other two. And it performed better nominally because the end result is that random forest tends to overperform clustering when you include everything. But as a point of note, opcodes, if you are just strictly operating on that code sequencing and you're trying to optimize your decompiler selection for clustering algorithms, then low-level IL of that out of binary ninja seems to be perform the best. Alternatively, if you can have access to all features, some keynotes. If you're still focusing on clustering world, P-code became the best performer, which was interesting. So as you add more features, the feature sets help differentiate or don't differentiate depending on the decompiler. So if you are able to use everything due to constraints or computation time or however you are, then maybe, and you want a cluster, maybe you should go to P-code. However, if you have infinite resources and you have infinite time and you want the highest number at all costs, then you would operate with a random forest classifier and you would use IDA-Pro's microcode, because when you consider all of the features together, the microcode is the deepest shade of red and it has the highest number and perform the best. This is the accuracy value. So this is the total, out of the total number of guesses, what is the ratio of guesses that are correct? This is your test accuracy that most people are familiar with when you got like a test back in school and it was like a 98% or however it is. And then we look at individual class performance. So if you are working with specific types of malware and they happen to be relatively similar to the malware represented in the training data set, we notice a few things. One, SIMDA was bad for all of them comparatively. And this goes back to that imbalanced data set that I talked about earlier of how you need representatively similar amounts of samples for a classifier to work appropriately. SIMDA had 42 samples out of 11,000. They just had a few amount of samples, so it's the why these numbers are so round because there's only so many guesses for 3 or 4 that got pulled in per batch, because training is done in batches. So it had lower numbers. It was not able to train on this class, and entirety showed its weakness there due to the imbalance. But if we're talking a more comparative example of, well, how do these decompilers compare versus the different model types? Worms, Ramnet. Worms had low values, especially in support vector machine. And you can see P-code having a significantly lower performance due to its lower shade of red in support vector machine for worm malware. However, if we look at SVMs and we look at obfuscated malware, it performed better. So there's a trade-off within one decompiler of, hey, I'm working with worms, so I should probably stay away from this one. But I'm working with obfuscated malware, so maybe I should go with P-code. And so this is how those different class scenarios end up working together. And this is recall. So this is the recall value. So this is, hey, I want to hit everything. So how many do I miss versus how many do I capture? Like, I can't let anything through, because we're talking about malware. So one single critical miss causes problems, which means recall is a really good statistic when you're thinking about your decisions past this point. Cool, so I've just showed a bunch of numbers and data. I showed some wonderful heat maps. What do you, as the observers of this talk, take away from what I'm saying? Well, if we're going to do this by like scenario, and you have a preferred reverse engineering tool that you're already using, because that tends to be how people make models, is they use what they're comfortable with, depending on which constraint, it determines what you should use. If you are working with support vector machines and you would like a more linear decision model, and you're prioritizing a balance of accuracy and precision, and you are also focusing on malware similar to the Vundo and Kelios, I can never say that word, Kelios version 1 families, Ghidra has the larger overall performance for those malware types for that specific use case. If you want Binary Ninja and you are working on a cluster-based model and you are prioritizing accuracy and you're only using those opcode sequences due to whatever feature selections or feature limitations you're trying to incorporate into a larger model, it seems from the observations in this testing that Binary Ninja's low-level IL will improve your performance. Likewise, if you are really trying to optimize your disk space and your space storage, because as you scale sample sizes, this could be an issue, and you are trying to get precision correctly and you can use everything, IdaPro seems to be the best. So there are performance considerations, and then there are space, time, money considerations. If you can't afford any of the premium tools, then you're stuck with Ghidra just because you have no money, right? Like Ghidra's free, it's open source, everybody can download it, and that's just a decision that you have to live with. Likewise, if your company's already bought into IDA, it's going to be really hard for them to either switch to Binary Ninja or Ghidra because they've invested so much as a technical debt into the IDA choice. And this is where justifying those different decisions via performance or via space savings might change management's decision, your personal engineering decision. Like, that's why this knowledge is important, because it empowers the engineer to make a more informed choice for their use case. To summarize, this is a nice, beautiful picture of Ghidra. Decompilers matter. Decompilers and the choice of which decompiler you use to exfiltrate data from binaries to train your machine learning models will change how your model performs. And it changes your model and how your model performs not in an insignificant way. After looking at the data, looking at the order of magnitude difference in data storage, these are issues that will scale as you ingest more data, which machine learning models, which operate on the scaling hypothesis, which basically just means more data, more compute, more better. Those issues will linearly scale and cause problems. Also, the intermediate language, because of how it is designed, will just suit different tasks, different malware better than other, depending on which malware you're trying to focus on. So this is the first half of my dissertation. This is one of two tests I'm trying to run. The first was this comparative study of this malware classification model. I'm working on a type recovery model right now. And then due to the advent of transformers, ChatGPT, all of these transformer models, another avenue of future work could be replicating these same tests with transformer-based binary analysis models. And that's just another avenue of future work. Once people have their car finalized and it's published and I can get the training data and see what they're doing. Because one of the big caveats of this comparative research is you need their code, you need the training data, you need to remove as many independent variables as possible so you can get a more accurate outcome. And thanks for listening to my talk. It was really great having y'all. If there are any questions, feel free to ask them, and I'll repeat the question for the stream, and I'll just do my best to answer it. Yeah, so it was the same percentage. I made sure that everything was the same. That's a really important question, because if I switch which is where, it could invalidate the numbers that are coming out. So it was really important to make sure that the same list was trained. So it was an 80-20 randomly selected split from all the classes, and then I just made sure that that split was fixed. So I trained everything on the laptop that was provided to me for my dissertation. So that laptop specs are an i9-1300H and a 4090 mobile. For those on the stream, the question was, what was the training split and what hardware did I use? Does that answer your question, sir? Yeah. Cool. Any other questions? Yes, sir. So the way Microsoft released the data is they said everything in here is malware. We're just trying to classify different types of malware. So we're trying to differentiate. Like, we know it's all malware. The question was, how did Chen's data include negative samples of not malware? And it did not. It was a pure, this is all malware. How do we tell them apart? And that was what was in the Microsoft Malware Challenge that Chen utilized as the training data for Chen's work. Yeah, so the question, again, for the stream was, did the training data used in Chen, which was released by Microsoft, include non-malware samples? And the answer to that question is no. So Chen's algorithm and Chen's work is the fixed parameter for this. And so when I'm trying to determine the changes between the different intermediate representations, I kept it in the box because we really wanted the apples to apples comparison. Again, for the stream, the question was, did I take these models outside of the boundary of Chen and test them on non-malware samples for a more real world functional value? And the answer is no, because we're trying to do the apples to apples comparison, and staying within the box of Chen so we identify independent variables was really important to me as a project designer. You're welcome. Yes, sir.
I've got a question from the stream. The question is, did any particular opcodes affect training? Is there a minimum number of opcodes that were inspected before a pass-fail is calculated in training, i.e. go-tos, jumps? Recording a sequence of instructions might not affect 20 instructions, but placed effectively could disrupt several hundred long opcode sequences.
Can you repeat the question one more time?
Sorry.
It's just a long question.
It is a long question.
Let me read this. Okay, so training-wise, no, because most of the binaries in the data set were substantially long. And when we came to developing commonality, those dimension vectors that I talked about, it cut out outliers. It was really trying to differentiate among common opcodes within the malware. So individual opcodes that would cause a single opcode foregram to act weird would have been cut out if it's only present one or two times. That doesn't mean that it's unlikely to be able to classify malware correctly if there's a rogue opcode, because when we're doing this comparison, we have several 100,000 millions of opcode groupings that had to get pared down to the 5,000 most common for the vector. So individual opcodes did not impact training negatively. And was there a second question that I peeked at?
The second question. Excuse me. Given your exploration of how decompiler architecture shapes malware classification, what is the most significant unresolved theoretical challenge within decompiler design that, if addressed, could fundamentally shift the landscape of automated malware analysis? And what novel architectural paradigm might hold the key to tackling it?
That's a deep question, man. That's a very deep question.
Do you want to read it?
No, I'm good. He basically just says, this is my interpretation of the question. What is the single missing piece that would fix everything? Is that the question was? Okay. So I think keeping, what's the word? Is it semantic equivalence between all decompilers and all intermediate representations identical? So you have a series of operations and they are semantically equivalent. It's really important. There was a paper written that I came across my research that tried to identify the most accurate IRs, or which IRs and intermediate representations and decompilers maintain semantic equivalence across all of them. So basically, they tested several, but for this example, there was 3 different decompilers. They tested all 3 of them for semantic equivalence, and sometimes, depending on if the code was weird, you could end up in a scenario where the decompiler had a non-semantically equivalent output. So the answer is 4, the answer is 4, for some reason the answer becomes 5 in the third one. And I think if you can solve that problem such that any design is semantically equivalent and has the same meaning to every other design on the output, then I think that would reduce a lot of these issues. Because if you have one person telling you the answer is one thing, and you have another person telling you the answer is the other, how do you make a rational decision between what you should act on? And so I think that's a really big hole that is difficult to fill because everybody has their own design paradigm, and everybody wants to make the newest, greatest standard and incorporate as many things, but if you incorporate too much and it changes meaning, you might have an issue. So I think that's the best way I can answer that question, is maintaining semantic equivalence between all decompilers would help. Yes, sir.
This is somewhat, it's semantic
Sure.
Earlier in your presentation, you had mentioned that Microsoft provided two
Yes,
file extensions. So
that is correct.
dot byte and the dot assembly.
Yes.
You said two files, and for me, I was just curious, how is it that they're so integrated that it actually effectively neutered the assembly? Because when I hear two files, I think you can tear one off and just leave it.
Sure. So the question for the stream is why are there two files? What is the .asm file? Why aren't they integrated correctly? If they're not integrated correctly, can't you just ditch one of them? And so that comes down to the sterilization process. The .asm disassembly file included information that was not present in the bytes file because it was just text. They could distribute that information. So it had more information, but it couldn't be converted to code because I just have a hex file, a hexadecimal file, and I just reinterpret it as a binary, then boom, they've distributed the malware. So the .bytes file that was used to generate the code examples is missing information present in the .asm file, but the .asm file is the file used to generate some of the other features that were included. Does that answer your question, sir?
It does, thank you.
Cool. Is that good? Awesome. Thank you guys so much. Oh, wait, we got one more? One more. So this is a great question, and I'm going to apply like a biology analogy to this. So if you're sick with the flu, we give you what is the flu? The flu. There's the flu medicine. It's the antiviral. Tamiflu. They give you Tamiflu. If you have an infection in your eyeball that has a completely different immune system, and they give you Tamiflu because you're treating all injuries as the same injury, then you're going to lose your eyeball. And so knowing which malware type is affecting your system is critical to triage and treatment and recovery of the system. So that's why knowing which one is, because the question was why does knowing what the type of malware matter? And so that's why knowing the explicit type matters. We good? All right, thank you all so much.